Good afternoon, everyone. My name is Nakaobi Hilda, and our project is Graph Reasoning Language Models for Soil Crop Informed Recommendation in Uganda Smallholder Farming, and this is Group 39. So the main goal of our project is to help Ugandan smallholder farmers choose crops using soil and climate data. The major problem that Ugandan farmers are facing today is that even when some of them try to carry out their soil tests for the pH, for the potassium nutrients that are in their soil, they don't know how to use this data. And hence they get poor yields after choosing a crop that does not fit into their soil properties. Our keywords are soil property assessment, which is checking for pH, nutrients like NPK. There is the texture. We have the organic matter content. Then the other keyword is crop recommendation systems, and these are tools to suggest best crops for soil and climate conditions. These are AI tools. Then there is knowledge graph reasoning, and here we are using a graph to link soil, crops, and farming rules for smart choices. Then there is fine-tuned large language models, and this is training AI to give accurate and local crop advice. Then there is resource-constrained agriculture, and these are solutions for farmers with limited money or tools. Then there is crop system planning, and this involves making plans for planting, fertilizing, and harvesting. And these are some of the related works, the works that have been done so far. We have the climate variability and agricultural productivity. They used Ricardian model, and the results were that poor farmers lose income due to climate change, and the adaptation, like better seeds can save income. The limitations of this context is that it assumes farmers can always change crops easily and ignore social rules in the village, which is impossible. Then it uses general data instead of local farm records, and the model runs slow on computers. There are more papers basing on the paper model results and content limitations and the architectural limitation. So our primary problem for the project is that smallholder farmers in Uganda and East Africa lack accessible science-backed tools to translate complex soil test results into actionable crop recommendations. And this results into suboptimal crop selection, yield gaps, and economic losses despite available agronomic knowledge. So basing on what I have said before, that farmers may receive the soil test numbers, and that is the pH, the sodium, and but they don't know what to use, like how to use the results they have gotten, and hence they get poor yields and lack a very good crop selection method. And our computational problems are there is constraint satisfaction, like how do we ensure AI recommendations never violate agronomic safety rules across thousands of soil crop climate combinations? There are very many crop climate combinations available. So how do we make sure that our AI that we have generated, that we have developed, never violates any rule, agronomic rule? Then there is heterogeneous data integration. How do we combine different data formats, i.e. soil maps, weather data, text documents, and taxonomies into a single system? We had a problem of different data sources and different data types. We downloaded CSV files, we had PDFs. So how do we combine all these different data formats into a single system? Then there was a hallucination problem. How do we stop large language models from generating false or dangerous farming advice? Then there was multi-objective optimization. How do you find planting plans that balance competing goals, for example, the profit, the cost, the labor, and soil health, with hard constraints that include budget and rotation rules? So there are very many stuff that are affecting farming in Uganda today. We have the labor costs, even the cost of the inputs, for example, the fertilizers. So how do we find the planting plans that balance these goals for the farmer, whereby they're within their profit range, their cost range, their labor range, and also the plan follows the rotation rules. The other problem is information extraction. How do you automatically extract numeric rules and relationships from unstructured scientific papers? We had very many PDFs, around 40 something PDFs. And how do we extract the numeric rules and relationships from these unstructured papers? Our research objectives were to identify soil and climate patterns for crops from different sources, to train various models for the recommendation system, to evaluate system accuracy for trained models for Ugandan farmers, and to deploy an offline tool for resource-constrained farmers. Then the questions we're asking ourselves were, what soil patterns affect crop growth in Uganda? Which models can be trained to recommend best crops for local soils? And how do soil nutrients and climate impact crop choices? And can knowledge graphs improve recommendation accuracy? And these were our research contributions and outputs. So we identified key soil and climate patterns from the PDFs that we had downloaded from FAO, ResearchGate, and many other sources, and agriculture databases to create crop selection in Ugandan farmers. We trained multiple models, and that was including the graph convolutional network and TransE, to recommend crops that match soil and climate conditions. Then we evaluated the accuracy of our models because we trained multiple ones, including the complex, we trained the graph set, and we evaluated the accuracy of all these models so that we are able to choose the best model that can apply here. And we deployed an Android app that helps resource constrained farmers get crop recommendations, planting plans, and affordable input suggestions. And this is our system architecture. We had the data input, that was the PDFs and the CSV files that we had downloaded from FAO. We had different files for the agroecological zones. We had files concerning the soil data. We had files concerning the weather data. And then we went to the step of pre-processing, and that was including the data validation, the data cleaning, the data normalization, the feature engineering, the PDF text extraction, entity recognition, relation extraction, and AI-powered extraction. For the AI-powered extraction, we use the Gemini API key to extract that data from the PDFs that we had collected. Then we proceeded to the knowledge graph construction, where we had the data integration, we merged data sources, we linked the entities available, the edge creation, the unified graph structure, graph storage, graph querying, and graph visualization. When we proceeded to the step of neural network training, and here in the training pipeline, we trained different models that included the TransE, the SMALT, the complex, either DCN, and the graph sage, and we evaluated these models, and we chose the best model that could best apply for our AI. Then we proceeded to the production system, and here we deployed our model. The web interface, the API gateway, the security layer, and many more. So this is our architecture description. We had data preparation, and our data was gotten from different sources that include the PDFs and CSV files, and they were processed using the Gemini API key, and this Gemini API key, it creates and cleans datasets just from the PDFs and turns them into simple triples. For example, the soil type crop rule. Then we had the knowledge graph construction, and these triples build a graph that links soil, crops, and rows, and it learns how to connect. Then we had the graph-based modeling, and the graph uses the graph convolutional network training to understand patterns, and we use the RAG retrieval augmented generation to find the best data matches. Then we go to the large language model layer, where we use the fine-tuned distilled GPT-2 model, which is the simpler version of the GPT-2 model. And this thinks about the data and generates crop suggestions. Then we have the application layer. The results go to the mobile app, giving farmers crop recommendations and plans. These are some of the architectures, the architectures of the models that we created and their mathematical foundations. The trans-E model, and this uses the head plus relation, and that is approximately equal to the tail. So the head entity, which is, for example, the soil type plus the suitable for, and that gives you the crop. And we train the distill modes, and this works better for the linear relations. We train the complex E, and this uses the imaginary numbers, more of the imaginary numbers to train. And then we train the GCN model 2. This is the architecture of the Gemini API, where we have the document checking after feeding our PDFs into the Gemini API. There is document chunking, there is initial NLP, then we proceed to the Gemini AI extraction agent, where there is prompt engineering, Gemini large language model, and there is few short learning. There's multimodal extraction, that's the text and table with the images. Then we proceeded to the post-processing and knowledge graph construction, where we had the validation and parsing, entity normalization, we had the triple integration, the graph database, and the embeddings. So our data that was in form of the columns and the rows, it was called the Uganda core data, and this was a structured spreadsheet detailing soil, climate, and crop performances in various farming regions in Uganda. It had 43 features, and that's covering from the NPK to the rainfall, to the organic matter, to the sodium contents, to the phosphorus. And the key features were nitrogen, rainfall, pH, agroecological zone, and each row is a complete suitability report for one crop within a specific region. The crops included maize, we had rice, we had cassava. Then the primary purpose of this data set was to provide technical, quantitative data for agricultural planning and analysis. And the other data set we had the literature review data, and this was gotten from different PDFs downloaded from different sources such as FAO and ResearchGate. We had data.gov, and we downloaded the PDFs from there. We had a total of 56 PDFs, and that's all the PDFs were containing agricultural data, and mainly for Uganda. We had soil nutrients like zinc, relationships between crops within those data sets, and each PDF had information attached to a given crop. Then the major purpose was to provide information regarding various crops based on soil data. This is the EDA, the crop distribution analysis, and here we looked at the number of times a crop is appearing in a certain PDF or a paper. in all the PDFs that we had. And according to our graph, we see that maize appeared most, followed by the groundnut, cassava, and stuff. These graphs help train the model to see how these graphs help the model to focus on what is important. And we had the crop distribution pie chart. This is how the crops were distributed across the PDFs, and we can see that maize appeared most, followed by the groundnuts and cassava. Then we had crops by average suitability. We had crops by yield potential. And we had the crop mentions, the number of times a crop was mentioned, soil mentions, the number of times a soil property was mentioned, and the management mentions. It was the number of times a relationship appeared. For example, the fertilizer, the irrigation, the disease and yield, and not a relationship, but a management form. Then we had the pH distribution by crop, and we had the nitrogen versus phosphorus by crop. We had the crop soil zone relation network, and this is the knowledge graph structure. And after training our models, all the models, and these are the results we got from the accuracy, the precision, the recall, and the F1 score. According to our metrics, our evaluation metrics, we chose the graph convolutional network because it had the highest performance according to the accuracy and the precision, recall, and F1 score. So we chose the GCN model, and this is the architecture of the GCN model. And this is our deployment pipeline. This is the demonstration of the developed products. And this is a sample of the data that we input. And this is what our developed product looks like. It has the AI analysis, the expert analysis, and it gives each crop a suitability score and its recommendations and constraints. And it also gives the land allocation plan. So in case a farmer has their piece of land, they are able to distribute certain pieces of land to certain crops so that they are able to earn income from all these crops. And according to our previous slide, the farmers are given a maintenance of these crops. So even when they plant all the crops according to the land allocation plan, they are already directed how to maintain these crops according to the recommendations and the constraints. We had these limitations, and the GCN architecture weakness is that it struggles with very large graphs, which limits its ability to handle soil-crop relationships fully. The suggestion is that we add more computing power. And then the GPT-2 was taking too long to fine-tune. So we had to fine-tune the Distill GPT-2, which took few hours, and it's more portable. Okay. Then that we had data gaps. The data set lacks complete micronutrient data. For example, zinc only appeared in 20% of the samples. Then this was affecting the recommendation accuracy. So the suggestion is that we collect more data from local soil tests or farmer surveys. Then the methodology constraints, the manual PDF extraction, and that was using PDF Plumber is slow and may miss some information. Since we had a lot of papers, this PDF Plumber is slow and could leave out some extra information that we could use. And the suggestion is that we automate extraction with advanced tools like OCR or faster updates. Then in conclusion, we created a reliable tool for smallholder farmers, and this tool uses soil tests and a knowledge graph with a fine-tuned GPT-2 model to suggest crops like beans or maize with plants for planting and soil fixes like lime. And this AI, it matches the expert advice 78% of the time. It has no rule violations and could increase yields with time in Uganda's challenging soils. Then the future works is that we could expand the knowledge graph with more local varieties and farmer field trials from all Ugandan districts. We could upgrade to faster graph models to handle various soil samples in fewer seconds. We could build a multi-language voice interface. For example, Luganda, Swahili, Nyankole, using on-device speech with no typing, since most of our smallholder farmers are local farmers in villages, and these people may not be able to type or read a lot of data. So we could build a multi-language voice interface whereby the farmer just sends a voice message to our AI and it replies with an audio too, and there will be no typing needed. And then we could partner with cooperatives to collect live soil data from farmers and auto update the system. These are our references and our acknowledgements go to our supervisor for his expert guidance and technical insights and continuous encouragement throughout the project. Thank you.